So last time we had started to talk about group operations. So this was just so if G is a group, X is a set, then an operation, an action of G on X was just a map. It's a map from G times X to X, G from X maps to G times X, which satisfies two simple properties. First, the identity element doesn't move the elements of X, and if I take the product of two elements in the group and apply them to any X, this will be equal to applying these elements in the corresponding order. Okay, so this is a very simple property, very simple definition, but it somehow is very often groups are viewed as groups of symmetries, and this somehow means via the action on something. In particular, we had used this to, so we had different such actions. We had the left translation by an element in the group, which comes just from multiplication, and we had used this to show Cayley's theorem, which I just made. Which just is that every finite group is isomorphic to a subgroup of a symmetric group, namely of the symmetric group as in as many elements as G has elements. The subgroup of SG. Okay, this is more or less, and this we did by using the action of G on itself by left translation. Okay, now we want to have another such thing, which is more, where one also can see what it has to do with symmetries. So we look at the dihedral group. So this is, so the group Dn is supposed to be the group of symmetries of the regular n-gon via rotations and reflections. So to make this more concrete and more precise, we just can, describe an element in the group, just how it acts on the vertices of the n-gon. So it just becomes a permutation of the vertices. So we view it Dn as a subgroup of Sn via its action on the vertices of the regular n-gon. So assume the regular n-gon somehow looks like this. For instance, n would be equal to 6. And we number the vertices 1, 2, 3, 4, 5, 6. And then we have the rotations. So the whole thing works like this. So this is an element which we call sigma. And we can also do reflection. For instance, we can do a reflection, along the, a line which is orthogonal to one of the sides. So we take, for instance, this one, this reflection, we would call tau. We can see that, if you kind of look at all possible combinations of these, you can obtain any reflection along any, orthogonal to any line, or also through any edge via some combination of the tau and the sigma, and you can make any rotation by doing several times the sigma. Okay, so let me write this down. So the rotation by the angle, what is it, 2 pi divided by n. So this is a regular n-gon. We call this is a permutation. Where every element is sent to the next one. So every vertex is sent to the one with one number higher. So this would be according to our thing. So we have 1, 2 until n. And so 1 goes to 2, 2 goes to 3, and so on. And the last one comes back. So and this I call sigma. And the reflection along the line orthogonal to the edge, say from n to 1, is what? Is as a permutation, it is tau, which is what? So 1 goes to n, and then always every element goes to n plus 1 minus the corresponding number. So 2 goes to n minus 1, 3 to n minus 2, and then n goes to 1. Okay, so these are two elements, and one can see that all the rotations and deflections can be obtained by combinations of these. So therefore, the dihedral group if you want to use as a subgroup of Sn is the subgroup of Sn. Generated by sigma and tau. Yeah?
Tau doesn't depend on the parity of
what I have written here does not depend on the parity. Depending on the parity, either in the middle one element is sent to itself or it isn't. But what I've written down does not depend on the parity.
Okay.
No, because if the number is which one is it? Is odd, I think. Then the middle one is sent to itself. But this I can still define tau like this. No, this just if this number would be odd, then it would pass to this, and so, but it still makes sense. So, we call that if S in G, in a group G, is a subset, then so the subgroup generated by S is the intersection of all subgroups of G which contain S. And so this I had mentioned, and as an exercise one can check that it can be described in terms of what one usually calls words in S. So that means I can write the subgroup generated by S as a set of all finite products x1 times xn, where n is some negative integer, so we have any finite product, and each of the xi we have that xi is an element of S, or xi to the minus 1 is an element of S. So the subgroup generated by S is the set of all products like this, where each factor either lies in S or its inverse. You can easily see that this will define. So this exercise is kind of trivial because it's easy to see that this defines the subgroup, and clearly it contains S, and obviously every subgroup that contains S must contain all these elements. So therefore this is simple. And so in particular in our case, so it's easy to see, and now I wiped it out, but you see the operations here, but from the picture it would also have been easy, so it's easy to see that if I take sigma so that the order of sigma is equal to n. So this is just the one which sends every vertex to the next. So after n steps you come back and not before. And we also have that the order of tau is equal to 2. So that means tau is equal to tau to the minus 1, and tau is not the identity. And that you can also see if you reflect once and reflect again, come back. And there's one more relation which is somewhat less obvious. If I take tau sigma tau to the minus 1, which is the same as tau sigma tau, then you can work it out here. You can work it out with this picture that I wiped out. So this was sigma, and this was tau. You can see that this thing is sigma to the minus 1. So it's a bit difficult to imagine, but if you first reflect, then you turn, then reflect again, you actually have turned in the other direction. And putting this together, then one can quite easily see that I can describe the n equal to the set of all sigma I tau to the j, where the I is between 0 and n minus 1, and the j is between 0 and 1. And this is actually quite clear from this, because we know that if I take sigma to the n, this is 1, so we need at most n minus the factor n minus 1. And then the tau squared is also equal to 1, so we get at least at most 1 tau. And if we can always put it in such a way that first the sigmas and then the taus, because if we have the tau on one side, we can bring it to the other side with this relation. Okay. So I could also because I could also multiply it by this and say that anyway. Okay, so this is anyway, you can work it out, it's an exercise. And it's also easy to see, for instance, if you just look at the definition here as perturbations, or how it turns this thing around, that all these elements will actually be different. So all these. It's also part of the exercise, but you can either check it from this or whatever, that these will never be the same. So all these elements are distinct. So in particular, you can see we have here n elements times 2 elements, so 2 elements. So in particular, we see, for instance, that if we take D3, this is the subgroup of S3, and it has 6 elements, and S3 has also 6 elements, so D3 is equal to S3, but D4 is contained in S4, and is strictly contained because this has 24 elements and this has only 8 elements. So the subgroup of index 3. Okay, so much for the moment for the dihedral group. We will come back to it. But in this case, we have defined the group via its action on something. And it becomes in this way subgroup of a symmetric group. So now I want to proceed a little bit with the definitions for actions. So in particular, there are some words to go with it. One is an action can be transitive. So transitive means, so if a group G acts on a set X, then every element of X can be sent to every other element by an element in the group. And simply transitive will mean that every element can be sent to every other one in a unique way. There will be only one which does it. Okay, so definitions. So the operation of the group G on X is called transitive. If just write in symbols for all X and Y in X, there is an element G in G, such that if I apply G to X, this gives me 1. So I can send any element to every other, and it's simply transitive. If this element G which does it will always be unique. So there's only one element with which I can multiply, which I can apply to X so to get Y. So if I write it out, and so unique, I write like this. G times X is equal to Y. So then
the first definition is
is equivalent to say that the quotient contains only one element?
Yeah, if you want. I mean, I haven't said what the, so the space of, there's only one orbit, yeah. I haven't yet said what an orbit is, but once I've said it, then it must say. Okay, and there's, so this, so for the, if you have a, so it's often kind of in particular in the French-inspired literature, instead of saying you have a simply transitive action, you also say that X is a G-torsor. So often X simply transitively on G is said as Gx on X, obviously, and that X is a G-torsor. This, there's one obvious thing that is almost true, namely if you have a simply transitive action, then it must follow that the number of elements in X is the same as the number of elements in G. This is almost true, namely if I choose one element in X, then I can send it in a unique way to any other. So this gives me bijection. But in order for this to be true, I need at least to have one element in X. So that means, so if Gx on X simply transitively and X is not empty, then we have bijection. So for any X in X, I can just say then the number of elements in G is equal to the number of elements in X. Of course, just the map. So when for a given X in X, the map which sends G to G times X is a bijection. And for instance, in number theory, it happens quite often that something is a G-torsor, and you would like to deduce that contains the same number of elements. And sometimes it happens, but very often it's impossible to prove that the thing is not empty. For instance, if you take some of the big things about conjectures about elliptic curves and millennium problems and so on, it has to do with such questions. Okay. I think in the notes I didn't write that it must be non-empty. Maybe I assumed implicitly that it does, or even I wrote somewhere that it's an action only if the thing is non-empty. But normally this is the definition. Okay. Yeah, maybe I should send you the notes. So I have some notes. I can maybe send them to you. They are very similar to what I tell you. Always a bit. Okay. So much for this. And then the other thing is what he mentioned. Other important notions for group actions are the orbits and stabilizer. So definition. So let the group G act on X. So, and let X be an element in X. The orbit of X is all elements which we can reach by applying an element of G to it. So this is therefore Gx is the set of all G times X with G in G. So this is a subset. Maybe I should maybe I call this Y to be less confusing. You don't have to know which one is large and which one is big. It's small. Okay. And so an element of this form I call an orbit. So G of Y is an orbit. If the orbit of all the orbits is a set of this form I call an orbit. a subset. What?
The group G is acting on the set X. Yeah.
Yeah.
So in the definition, we need to put G point X such that X is an ombre and X not. No.
Well, here I put the element I put.
In the set, and the definition, and the.
Oh no! It's the orbit of an element y in X.
Ah, okay.
No, I said take y. In X.
Ah, okay. So okay.
Yeah. Okay. Yeah, I changed the notation so that confused it, but okay. So, and as he said, as you said a moment ago, by definition, the action of G on X is transitive if the orbit of, say, y is equal to x for all elements y in X, which is the same as for any element. So the group action also defines an equivalence relation on X, whose equivalence classes are the orbits, and then we can look also at the space of orbits. So
How we can do that?
what?
It will be transitive if G of y equal x for all y.
Yeah, that's what I. So
Did it
what?
obvious by the definition?
Yeah, because so the definition here says that any element, maybe x or any. So here I call it y. Maybe I perhaps should have called it x. But anyway, any element x can be sent by G to y, to any element y. So that means the elements of x that I can reach from my given element y by applying an element of G are all of x. And this is precisely the object.
Represent all x like G dot something.
Yeah, yeah. So we have this equivalence relation, so we define an equivalence relation on X. Maybe check one like this on X by saying that X is equivalent to Y if and only if they lie in the same orbit group. In other words, if and only if there exists an element G in G with G times X is equal to Y. Now, this clearly is an equivalence relation, just from the fact that we have an action. Obviously, every element is equivalent to itself. We're taking the identity. If I take the inverse, we see that if X is equivalent to Y, then Y is equivalent to X. And if I take the composition, the product of these things, I get the transitivity. So this is clearly an equivalence relation. And the equivalence classes, by definition, for this equivalence relation are precisely the orbits. No? So it plays a role. So I'm not really going to use it, but it's similar what we have done for subgroups and whatever. So the set of equivalence classes G on X and denoted X divided by G. So, and this, well, we're not going to use it in the lecture, but it happens often in mathematics. One studies this. The other notion which is important, in addition to the orbit, is the stabilizer. So, the stabilizer of an element small x in X is the set of all G in G which do not move it. So that G times X is equal to X. So we have that our G X on X, and so the stabilizer of an element X in X is so usually I will denote it by Gx, although it's slightly confusing because it's rather similar to this. So if one needs to know more, I could say it's the stabilizer of G in X. And this is, so this is just two notations for the same thing. And this is the set of all G and G which do nothing to X. Okay, so this Gx is clearly a subgroup of G, because if two elements do nothing, their product does nothing, and whatever, I mean, follows directly. So Gx is a subgroup of G. Okay, and we can relate the stabilizer G and the stabilizer to the orbit by following simple lemma. Namely, so G is still acting on X, and we take an element in X. There is a bijection. From G divided by the stabilizer of X, so the set of cosets, to the orbit of X, which sends the coset corresponding to G to G times X. Okay? So in particular, the number of elements in the orbit is equal to the index of the stabilizer in G. Okay, and so why is this the case? That's so this is at least if Gx is finite. Otherwise, so we have to show that this map is well defined and injective, and it's surjective by definition. So the map, which I've just defined, G times Gx maps to G times X, is well defined and injective. So that means that two elements here are in the image are the same if and only if here they were the same. And so let's just see it. So G prime G is equal to G So Gx. Well, I can multiply, for instance, by g to the minus 1, or otherwise I can multiply back. So this is if and only if g to the minus 1, g prime, gx is equal to gx, so this is the same. If this lies in the stabilizer. So this means that g to the minus 1 is equivalent to g to the minus 1 g prime times x is equal to x. And now I can apply the inverse here, and so I get this equivalent to g prime x is equal to gx. Okay, so this shows the map is well defined and injective. And if you look at the definition here, it is surjective by definition, because every element g in G occurs here. I mean, obviously only if it's well defined, which we've just seen. Okay. So this allows us to state and prove the so-called orbit stabilizer theorem, which is a very trivial result, but it's also very useful. So this is a very easy consequence. It says, so assume that g acts on a finite set x, and we take a system of representatives, so let R in x be a system of representatives for the orbits. Representatives for the orbits. And by this I mean that it contains one element from every orbit. Precisely one element from every orbit. Then the number of elements in X is equal to either the sum over all X in the system of representatives of the number of elements in the orbit, or it's also equal to, again, the sum over all X in R, the index of Gx in G. Okay, so there's okay, so this is so one uses this very often, but by itself it's totally obvious. It's just a reformulation of what we just said. Because the first thing is that the orbits are the equivalence the equivalence classes of an equivalence relation on X. So therefore, X is the disjoint union of the orbits, and so the number of elements in X is equal to the sum of the number of elements in the orbits. And we know that we have just seen that the number of elements in every orbit is this index. So we have, so it's basically, so the proof is, we have already done. Okay, so much for the orbit stabilizer theorem. So now I want to briefly talk about the action by what happens in this case if we look at the action by conjugation, and we want to apply this to then show that if I have a group of order p squared, if p is a prime, then it's necessarily abelian. We know if p is a prime number and you have a group of order p, then it's cyclic, so in particular it's abelian. But if now the number of elements is p squared, then it doesn't have to be cyclic, but it will be still abelian. So let's briefly talk about this action by conjugation. We'll also formulate a version of this orbit stabilizer theorem for the conjugation action, which is what is called anyway well, could come. So we look at the action. So let's say addition. So if G is a group, if I take elements G and H in G, we say that say G is conjugated to H if there exists an element A in G such that, what is it, say H is equal to A to the minus 1. Okay? So this again is clearly in the equivalence equation. And in fact, we have an action of G on itself by doing this, and the equivalence classes eigen that we have here are the orbits. And so the equivalence classes G with respect to conjugation are called the conjugacy classes. In fact, somehow the conjugacy classes are important invariants of the group. I mean, somehow, for instance, if a group is finite, if two groups are finite and they are isomorphic, so obviously they have to be bijective, but they also would have to have the same number of conjugacy classes, and maybe the conjugacy classes have to have the same properties. So these are important invariants. See later. Anyway. So we are also interested so conjugation obviously has something to do. So you see if G and A commute with each other, then the conjugation does nothing. And so it has, this conjugation action has much to do with how the elements in the group commute. So in particular, if we have an element in G, we could be interested in all the elements which commute with it. So the centralizer of X in G is denoted Z of X, and it's the set of all G in G which commute with X. So again, clearly the centralizer of X is a subgroup of G. Because if two elements commute with X, then their product does. And actually maybe it was at one moment, but okay. And it's also clear that the center of G is a subgroup of the centralizer of X for all X and X. Because the elements in the center are the elements which commute with every element in G, so in particular with our given X.
This is a subgroup of this, or is this?
What? No, the center is a subgroup of this because it's smaller. These are the elements which commute with everything.
Ah, okay.
And these are the elements that commute with X, so this could be more. And it's also clear.
X in G.
What?
X in G.
Yeah, there's no X. It's also clear that if the if X is in the center of G, then the centralizer of X is equal to G. This is just a reformulation. Every element commutes with X. Okay. So these are just some stupid combinations. So, and now let me reformulate some of this in terms of an action and then see what I can do this. So, as I said, this conjugation is an action. So, so the conjugation action of G on itself is the action G H maps to G H G to the minus 1. And it's clear by our definition that the orbits of this action are the conjugacy classes. Analysis of X of G. Okay. And then we have basically a reformulation of the orbit stabilizer theorem for this conjugation action, which is usually called class equation. So again, the orbit stabilizer theorem was kind of obvious, and this is a special case of it, so it's also obvious, but it's used very often because it's can often be simply applied. And one, in some sense, always formulates it in a slightly more complicated way than would be necessary, but it's more practical to use in this complicated way. So let G be a final group. And so we take R, a subset of G, which is supposed to be, a system of representatives for the conjugacy classes, but only for the conjugacy classes which do not lie in the center. So that means that R in G be a subset such that every element in G without the center of G is conjugated to precisely one element in R. then we can again say the number of elements in G is given by this simple formula. So then the number of elements in G is equal to the number of elements in the center of G plus the sum over all x in R, the index of the centralizer of x in G. So maybe should have okay, so let's see that. So I want to somehow reduce it to this object stabilizer theorem. So let instead R prime be a system of representatives for the orbits of the conjugacy, or for the conjugacy classes. So, for the conjugacy classes. Of G. So one element from every conjugacy class. So this I call R prime. Then by the orbit, this is the same as the orbits of the system of representatives for the orbits of the conjugation axis. So then by the orbit stabilizer theorem, we have that the number of elements in G is equal to the sum over all x in R prime of the number of elements in the orbit of x, with respect to the conjugation action. And so, action by conjugation. And then I claim that this is the same as the index of the centralizer. So this is just because, if you look at the definition, which the definition of the centralizer, these were all the elements which commute with x. So this is precisely the stabilizer of x under the conjugation action. Because d of x is equal to gx for the conjugation action. And then clearly, if I have an element which lies in the center of G, then it commutes with every element, so the conjugation does nothing to it, so its orbit consists only of y. So therefore we see, it follows that the center of G is a subset of our set of representatives R prime. So it's just the, and for the elements there, we have just that this is always 1. So we get that G is the sum over all, first elements. So it's supposed to be the sum over all elements in R prime, which contains, for one thing, elements in the center. If we are in the center, then the orbit only has one point. So it's just 1 plus the sum over, we take all the system of representatives of the orbits which do not lie in the center, which is our R from the theorem. And then we take what's written here. And that is the orbit stabilizer theorem, the class equation. Okay, so this is just this statement. And now I wanted to come about this thing about the groups. So of order p squared being abelian by using this class equation. So first a little bit do something slightly more general. So if p is a prime number, so we call a p group a group such that if the order of elements is a power of p, the positive power of p. So a p group is a group of order p to the n for some n bigger 0. So positive power of n. So we know, as I said, we know that the group of order p is cyclic. We want to show that the group of order p squared is abelian. For this, we first show the following: that if I have a p group, then its center contains at least p elements. So, there are certainly groups whose center just consists of 1. But if the group has p to the n elements, then the center is not just trivial. It contains at least p elements. So the center of a p group has order at least p. This we do by applying this class equation. So let G be a group with p to the n elements. So then we know that the center of G is a subgroup of G. So it means that the number of elements in the center must divide the number of elements of G. So that means the number of elements in the center must be power of p. So thus, number of elements in set G is equal to p to the k for some k bigger equal to 0. Obviously, it could also be just one element, which would not help us. So now we look at the class equation. So the class equation is written here. So is this, and where this R is a system of representatives of the conjugate classes not in the center. So therefore, if I have an element, so if X is in R, then this element does not lie, X does not lie in the center. So that means it doesn't commute with every element. So that means that this subgroup here is not equal to G. So, X is not plus CX strictly contained in G. So as
does not belong to center.
what? Yeah, I meant not. I also said it, but I didn't write it. So, so this is strictly contained in G. It's a strict subgroup. So that means, as it's a subgroup, the number of elements divides G. So first, divides G, and this index is a positive power of P. So it's divisible by P. Or no, because the total thing is P to the n, and this is some. This is smaller, so it must be, and it's a divisor of it, so it can only be some power of P. And we also know that the number of elements of G is a power of P, so it's also divisible by P. So also G is divisible by P. So we have the left-hand side is divisible by P. Every summand here is divisible by P, so all this is divisible by P, so therefore also this is divisible by P. We know that this, the center can never be empty, so there's at least one element, because the identity element is always in the center. So it means the number of elements in the center is at least P. Obviously, it must be a power of P because it's a subgroup of P to the n. Okay. So now we can do this thing with the boolean. It's an easy, simple consequence proposition. That so P is a prime number, so every group of order P squared is a boolean. So we somehow have to show that every element commutes with everything else. So let's say we be a group of order P squared and show for every element X in G, the centralizer of X is the whole of G, because that means every element commutes with every other element. So alternatively, you could also say that every element lies in the center. So in some sense, by way of contradiction, we assume that X, so if X is not in the center, we'll see later that in a moment that this cannot happen, but let's assume X does not lie in the center, then if I take the centralizer of X, this contains obviously the center of G, because every element in the center contains with everything, but it also contains X, because X commutes with itself. And X does not lie in the center, so it follows as the number of elements in the center is at least P, that the number of elements in Z of X is at least P plus 1, and as this is a subgroup, it follows that the group at Z of X is equal to G. And so that's fine. And well, and if x is in the center, then it anyway computes removes everything, no? So that's also fine, because an element in the center commutes with everything. So in some sense, basically, we have assumed that x does not lie in the center, and we have shown it does. Okay, and so this shows that this group is abelian. Okay, so much for the moment about these group operations. Now I want to a slightly different topic and talk a bit more about the symmetric group, describe it a little bit more explicitly, also say, for instance, what the conjugacy class in the symmetric group is. And first we start by describing the elements in the group, in the symmetric group in another way, in terms of cycles. So a cycle is a permutation which sends one element to the next, and so on, the last one comes back. And so every element in the symmetric group can be written as a product of cycles. Oh yeah, of disjoint cycles. Yeah. So let's do that. So we come back to the symmetric group. So let me first define the cycles. So we take some elements. So let A1 to AR be some distinct. So it's an R element in the set from 1 to n, on which the symmetric group acts. So the corresponding cycle A1 to AR is the following, so is an element in the symmetric group. This is the following permutation. So is the permutation sigma in Sn, which has the following properties with. So in all of these cases, if I take sigma and apply it to AI, this is AI plus 1 for I from 1 to R minus 1, sigma of AR is A1, and any element in 1n which does not is not among these is sent to itself. Okay, so this is this cycle. For instance, if the cycle is 1, 2, 3, then the map is the corresponding. It is the map which sends 1 to 2, 2 to 3, and 3 to 1, and fixes everything else. We should note that this is not somehow unique. You can write down the same cycle in different ways. You can kind of turn it. So if you have so A1 to AR can also be written as, say, AL plus 1, and so on until AR, and then A1 until AL minus 1. So you can just, instead of starting with the first one, you start with the else one and then turn around to the second. So the notation is not completely unique, but it's otherwise. Okay, so just a few more words. We call R the length of the cycle. A1 to AR, no, as many elements as there are. And you also say it is an R cycle. By definition, a one cycle is just the identity. No, it sends one element to itself and the other ones to itself. And the two cycles are called transpositions. So therefore, transposition will exchange two elements and leave everything else fixed. And I also say that two cycles are disjoint. Maybe AR, B1, and BS are disjoint if the corresponding sets are. If they have none of these elements is in common. This one. So these are just these definitions. Now, we want to say that every element in the group can be, in a symmetric group, can be written as a product of cycles, disjoint cycles. So this is called cycle decomposition. So every sigma in this n is the product so sigma is equal to, say, sigma 1 times sigma s of pairwise disjoint cycles. No two of these cycles have a point in common. And so this is the main thing here, and then some simple observations. If I have disjoint cycles, they commute. So sigma tau commute, so that sigma tau is equal to tau sigma, and every element in Sn can be written as a finite product of transpositions. In particular, Sn is generated by transpositions. Is a finite product. Okay, so these two are quite simple. Let's here with one, which we do by doing some group action. So let's look at our group sigma, our element sigma in Sn. We want to write it as a product of these things. And we do this by looking at the subgroup generated by sigma and looking at the orbits of the subgroup on the set 1n, and basically the orbits will correspond to these cycles. So let's do it so that H subgroup generated by sigma, so cyclic subgroup of Sn generated by sigma. So then we have an action of this subgroup on the set 1n. So then we have an action times from H times 1n to 1n by just applying this element in the symmetric group to the element in 1n. So any element in H, tau, if I apply it to some number k, this is sent to tau of k, just as an element in the symmetric group. Now obviously, if we have the whole symmetric group acting, then it will act transitively on set 1n, but if we just take the cyclic subgroup, then there will be some orbits. So we choose some elements, say V1 to VR in 1n, such that so that the orbits of these elements are the different orbits. So such that H of V1 until H of VR are the different H orbits on set 1. So if we have this, this is, if we just take the powers of sigma, at some point the power of sigma has to send our element b I to itself, because one thing, a very high power of sigma will anyway be the identity, because it's a finite group, but at any rate it could also happen earlier. So for all I, so from 1 to r, let mi be the smallest number such that if I apply sigma k times, so I write the sigma to the k, so sigma composed with sigma applied to bi is equal to bi. So I take the smallest power of sigma, which sends bi to itself. This number I call mi. So then, first, if I take pi, sigma of pi, and so on to sigma to the mi minus 1 of pi, these are all distinct. These are mi distinct elements, because if there would be two which are equal before, I can kind of divide by the corresponding sigma. So if sigma of L pi is equal to sigma of S pi for 0 smaller L smaller equal to S smaller than mi, then I can multiply with the corresponding inverse power of L. So then it follows that Pi is equal to sigma of S minus L Pi, which is a contradiction to the choice of the Mi minimum. So these are all distinct. And we saw somehow, we can see obviously that no other elements, so if we apply powers of sigma to Bi, we will only get these elements, because now we are back to Bi. If we apply sigma again, we get this. So thus we get, so we have that if I take the orbit of Bi, this is just consists of Bi, sigma of Pi, and so on, until sigma to the Mi minus 1 of Pi. And if we apply sigma again to this thing, we get Pi. So it means that, and if we call sigma I to be this thing, this is an Mi cycle. And these cycles are disjoint because, for different i's, because the elements in the cycles are the orbits, and the orbits are disjoint. So, and sigma I are disjoint cycles. Then this goes up. Also almost done. So finally, I claim that sigma is the product of that. So maybe, whatever. Was it S? Or was R maybe? So if I take any element x in 1n, then I have to see that the sigma does the same to it as this. So then, as the set 1n is a disjoint union of these orbits, it means that x lies in precisely 1 h of Bi. So that means there exists unique I in 1R in such a consistent lies in the corresponding orbit, and unique K in the set 1 to what is it? 0 to Mi minus 1, such that x is equal to sigma to the k of Bi, because the corresponding orbit of Bi just consists of these powers, and so I can write x like this. So then, if I apply sigma to x, this is the same as sigma I of x, because sigma I sends x to sigma k plus 1 of x. by definition, because the map is just sending it to the next. And if I take sigma j of x, this will be, sigma j of x, so this is a different cycle, so which is disjoint to it, so this is the identity, or this only acts on the orbit of, is only non-trivial of h of bj, so sigma j of x is equal to x. And also sigma j to apply to any power of sigma I of x is still equal to x, because this still lies in the same orbit as x. So thus, so for all j different from I, so thus, if I take sigma of x, this is equal to sigma I of x is equal to sigma 1 times sigma of x. So here on A. So I decide to mark carefully, but it's okay. Maybe I can finish this because the rest is trivial. So this shows 1, and 2 is obvious, because if I have disjoint cycles, then if I apply the product of the two in one direction on the other direction, one moves only the things which are in the support of sigma, and the other one only in the support of tau, and so they can't do anything to each other. And the third one, I just have to show that I can write any cycle. So as I know now that every element in Sn is a product of disjoint cycles, it's enough to show that every cycle can be written as a product of transpositions. And so let's just do that. So we have, if I take, for instance, A1 to AR, I claim I can write this as follows. Maybe I write A1, AR, A1, AR minus 1, and so on, A1, A2. Because if you just do it, so you apply it from here, so 1 goes to 2, and then all the rest doesn't do anything to it. And then here, so the next one would be 2 goes to 3, and then nothing happens to it, and so on. So this is just this. And so we have written this cycle like this. Okay, so maybe that's enough. So we see each other on Friday. Maybe I will try to also send you some homework today. If I still have 1 hour to do that. Okay, so we see each other then. Have a nice